Okay, I now have 9 a.m. Mountain Standard Time here on my clock, so I think we'll be ready to begin. My name is Cody Weber with Electromagnetic Applications. I would like to thank everybody for joining this webinar and to welcome this large group of engineering professionals. We have additional information about this webinar, and possibly a portion of this presentation will be uploaded to our website following this session. If at any time during the presentation you have questions about the material, my colleague Jennifer Ketagorski will try to answer those questions. On your WebEx screen you should have a Q&A box. If it's not displayed already, there should be a button in your upper right-hand corner of your WebEx window where you can type in questions, and she will try to address those questions as we go along. If there are some questions that she thinks would be pertinent to address to the whole group, she will sort of flag me, and I will try to answer those questions to everybody. If you have questions after the webinar, you are more than welcome to contact us via email. On this screen you can see my email, cody@ema3d.com, Jennifer's email, as well as Tim McDonald's email. If you have any questions about the content of this webinar or additional questions or suggestions for us about this webinar, we'd be happy to address those. One other thing is that when you exit the webinar, you will be prompted with a very brief survey, and we ask that you please fill that out to help us with any feedback that you may have. And as this screen displays, for this presentation, it is a webinar. We intend to begin a webinar series here at EMA where we provide an educational series on varying topics for a range of different electromagnetics problems, such as HERF, lightning, EMC or EMI, and we intend to continue this additional information on our website at ema3d.com. We have information up there now, but you can expect to see more information about these webinars on our website. So let's begin the presentation now. It's designed to be very informative about the topic, and it's about an hour long. And so if you have questions, like I said, please enter them in the Q&A box during the session. And if you have additional questions afterwards, you can, of course, email myself, Jennifer, or Tim, and we'd be happy to talk to you about it. So the topic of this webinar is the validation of CEM simulations to support aircraft certification projects, and it covers both the direct and indirect effects of lightning. So the contents of this webinar are an introduction, typical certification steps, the lightning environment and existing documentation, computational electromagnetic simulation tools, the validation of these CEM simulations, and a discussion on margins. We provide a couple historical examples of CEM validation. And then the main portion of this webinar is to review a recent publication of CEM validation results that was done for a large-scale commercial aircraft project. And it includes comparisons of simulation and experiment for a test box and a full-scale aircraft. And both of these items had topics on the direct and indirect effects aspects. So for computational electromagnetic simulations, there are typically two main reasons for doing those types of simulations. One is for certification support, which we would demonstrate in this webinar, and that's to help develop a complete understanding of the electromagnetic response of a particular aircraft design. And by doing this, you're also allowed to reduce the total number of program tests and use your simulation outputs to guide your test inputs. Another reason to do the CEM simulations is to aid in the aircraft or system design evaluation. You can run simulations and determine if there is a need for additional protection or see if you can modify your current design in any way to achieve the necessary protection. Both of these stages of simulation can provide a great cost benefit to your program. So on the topic of lightning, there are many, many references available. I'm not going to talk about each of these. If you have any questions about the lightning references or would like a copy of this list or additional information, please contact us. Some of the very useful documents shown here sort of flow together in a sequential manner, and we have put together flowcharts that outline this structure. And if you're interested in that, we can help guide you through that or talk to you about it offline. So when we talk about lightning effects, it's typically broken up into two categories, either direct effects or indirect effects. And direct effects relates directly to the physical damage of the vehicle or system. And it's often verified by representative coupon tests. And the items that are included in direct effects are the melting or burning of attachment points, resistive temperature rise, magnetic force effects, acoustic shock waves, arcing and sparking at bonds, hinges, or joints, and the ignition of vapors within fuel tanks. 5 and 6 are in bold print because CEM simulations can be used to support these two aspects of direct effects. And you can use your computations to establish expected current density levels for your coupon testing, and also to analyze other aspects of those. For indirect effects, it pertains to the electrical transients that are induced by lightning in aircraft and electrical circuits. And this is often verified with bench tests on cable harnesses, either in the aircraft structure or on a separate bench test. And oftentimes the threat levels and waveforms used on these tests can be guided by simulation. So in a certification project, there are typical steps involved. They may vary depending on your project or your particular application, but these are some common steps when doing lightning certification. Whenever you have a vehicle, you need to initially determine the lightning strike zones, and we'll talk about that on the next slide. You also have to establish the external and internal lightning environment, and this is where your CEM simulations are of great benefit. They allow you to completely analyze the vehicle or system that you're looking at and understand the lightning distributions throughout that entire vehicle or system. Other steps that you have to do are to identify flight critical or essential components. For direct effects, you have to identify all possible fuel ignition sources. You must have a plan to establish protection criteria necessary to meet your safety guidelines. You also have to design that lightning protection and then verify it or the adequacy of your design. And there's a few ways you can do that, either by similarity to other proven designs. You can do a testing program either on coupons that are representative of your vehicle or systems or the actual aircraft structure itself, or you can put together an acceptable analysis. Those are sort of the typical 3 ways that you can verify the safety of your design. In this webinar, we will cover some of these steps, but we will focus on the CEM in aiding the certification process. So here's an example of a lightning zoning for an aircraft. This is taken from ARP 5414. It allows you to determine the lightning attachment zones and determine established threat levels. You would use these appropriate waveforms to evaluate the different portions of the aircraft. The table in the lower left-hand side shows that for a particular zone, like 1A, you can see in the right-hand side, it's flashes that go from the lower left to upper right, which is typically at the extremities, the wingtips, the engine, the nose, the stabilizers. Those are zone 1A, and you would determine the appropriate waveform, voltage or current waveforms that you would apply to that zone. And here's a sample of one of those waveforms. This is given in ARP 5412 for the lightning environment and related test waveforms, and this is the idealized standard external current waveform for component A. It has a peak amplitude of 200 kiloamps at a time of 6.4 microseconds. You can see the exponential equation used to produce this waveform on the right-hand side. So when doing computations, there are many different simulation techniques and there are many different software tools available. The IEEE standard 1597.2 is a very good reference. It has sections in that standard that discuss all of these different simulation techniques as well as many others and help guide you on which simulation technique is appropriate for your particular problem, as you would want to use a particular technique depending on the problem that you're trying to solve. And it turns out for lightning transient problems that the finite difference time domain technique is well suited for that. And what we use is EMA 3D, which is the software that we have maintained for the last 30 years. It is very mature and is very well suited to solve lightning interaction problems for complex and inhomogeneous aerospace applications. Some of the benefits are that it can capture the electromagnetic details of an entire aerospace or ground system down to individual electronic interfaces. We can resolve pin details for full aircrafts or large ground systems. And we do that with an integrated M-harness program. It is a transmission line solver that we co-simulate with our 3D model, and we do that to accurately capture the individual pins at the interface level. This EMA 3D also has some very valuable computational speed-up techniques. Parallel processing is available both on Windows and Linux machines, and we have a permittivity scaling feature that we can increase the permittivity in a problem space in a gradual manner so that it does not perturb the solutions of lightning transients. And when we combine these two speed-up techniques, we can get factors of up over 100 times for our simulations, which in the case of lightning, when you have large-scale problems and you need to run them out for a relatively long time, hundreds of microseconds, this speed-up is of great benefit to that. So in that IEEE standard, there are discussions about CEM validation techniques. And if you read through that document, you'll find that there is no actual standard that specifically qualifies CEM simulations for lightning interaction problems. It has, as I say, a lot of useful information, but it's more geared towards EMC applications. And it typically uses the feature selective validation, FSV approach, which is you have to do a transfer, Fourier transfer into the frequency domain, and it's not really well suited for lightning transient problems. But there is an overall validation approach that's outlined in that document that does apply to lightning interaction problems, and that's where you have to go through these 3 levels of model validation. Level 1 is the mathematical level, where you have to evaluate your computational technique. Is the method I'm using, finite difference time domain, FEM, method of moments, whatever it is it correct? Step 2 is the implementation level. Does the code or software that I'm using accurately solve Maxwell's equations? And then level 3 is the model level, where you have to do specific model validation. So are the parameters, the assumptions, and the setup for your particular problem, are they appropriate to solve the intended problem? And you also will have to establish margins associated with this validation. So anytime you do a validation, you'll need to have margins that are applied to your results as a sort of a safety margin. So some approaches for validating the CEM to lightning transients are to, what we have done in this work and has done elsewhere is to compare peak magnitudes in a dB scale and also look at the similarity of waveforms. So this uses a peak magnitude comparison and a visual inspection of the waveforms for correlation purposes. There's some publications available that outline the shortcomings of the FSV method for transient pulses. If you're interested in those, you can contact me and I'll give you that information after the webinar. But basically, they propose a new validation technique called the transient time domain validation technique. And to me, it seems like a very good approach. I have not yet tried it, but it's an interesting alternative to just peak magnitude comparison or the FSV method. What it does is it compares the experimental and simulated data in the time domain. It uses three primary indicators: the maximum amplitude level, the maximum rate time, and energy contained in the signals. And the approach combines these three indicators to establish a total error average to get a quantifiable value to evaluate your overall validation. So margin development is a very important part of the validation process. And with every effort, you must validate or determine the accuracy of your simulations. And oftentimes, this is done through an experimental comparison. Important to keep in mind, especially for lightning problems, that it may be difficult to apply a single margin to simulation results for an entire aircraft. Sometimes the probe correlation will depend on the magnitude and coupling mechanism of that particular probe. So if you're looking at different areas, you may have different coupling mechanisms. If you have wires routed on the trailing edge side of your aircraft, you may have some inductive coupling when your control surfaces, your flaps are down and your spoilers are up. Magnetic fields can directly couple into those cables, and you may have a dominant inductive or magnetic field coupling. If you have wires inside of your leading edge or pipes inside of your fuel tank, diffusion or resistive distribution may be the dominant levels. And so depending on the type of probe you're looking at and the dominant coupling mechanism, you can get very different correlations between your simulations and experiment. When you're looking at fields on the outside of your vehicle, you can typically get very good accuracy with your simulations, oftentimes within 3 dB of an experimental measurement. And when you look at currents inside of metallic structures, inside of a leading edge or something else, these magnitudes can be very small, oftentimes less than 0.1% of your injected current. And you can have differences between your simulation and experiment that are greater than 10 dB. But in these cases, you can still consider that a good correlation because the simulation is predicting that there will be small currents at those locations, even though the exact amplitudes and waveforms may have some discrepancies. One important note in the standard, IEEE standard for CEM validation is some comments about experimental data. Oftentimes, the repeatability and accuracy of measurements, well, every time, they are very important. And it's important to keep in mind that for EMI or EMC problems, measurements can have uncertainties as well. And it's important to understand that the experiments can be wrong just like the simulations can be wrong. And it's necessary to avoid what they call a measurement bias. And in my experience, it seems to work best for the validation and analysis effort when the testing and simulation are used together to understand all aspects of the lightning coupling to your particular vehicle. And so there's some things that you can quantify experimentally that you can use in your simulation inputs, and there's things that you can understand in your simulation that can help guide your testing program. So that's an important aspect to keep in mind. One example of a margin development for a recent certification project is for the A350. In that program, they used an extensive amount of finite difference time domain simulations to evaluate conducted currents throughout the structure of the A350, and they applied safety margins to these simulations based on a sliding scale depending on the current level. And so this publication was released at the most recent ICOS conference in Toulouse, France, and they describe how they use very small margins for high-level currents that are simulated with high accuracy, and that for low levels, they indicate there are many more variables influencing the results, and they have a lower overall accuracy, which we have seen as well. And for these cases, they establish a minimum or floor level of current that will be used to encompass all low-level current tests. So then rather than setting individual magnitudes for all of your low-level coupon tests, you pick a value that encompasses all of those and apply it, which is seems like a very logical approach to me. So now we'll move on to some examples of where CEM has been used in certification projects. EMA 3D was used on one of the first composite fuel tanks, and this was for the Saab Gripen fighter. The image shown in the right is a sort of a wing box, test box as it's described, and it's for carbon fiber upper and lower skins. The results of this analysis are published in both ARP 5415, which covers indirect effects of lightning, and in the Lightning Protection of Aircraft book. You can see for this case they did a peak magnitudes comparison, and some of those results are shown in the table on the lower left-hand side. Overall, you see a very good or very similar magnitudes between the measured and calculated values. Another example is for the MD80 program, where they use simulations compared to test data to help certify the MD90 by simulation. There was a lot of similarity between the two designs that they were able to use a lot of simulation to bypass testing and use a combination of similarity and analysis to go through their certification process. And you can see a sample waveform in the lower left, and in the lower right table, you can see some of the ranges for variation from measured values. So they were getting comparisons between simulation and experiment, typically within 15%. A more recent example is for the Mitsubishi Regional Jet. They have been using EMA 3D, and they published some results for a test box, which is aluminum wing test box, and they had a dramatic successful correlation between experiment and simulation for many number of probes. And within that publication, they show a few of their results, and these ones displayed here are surface magnetic fields at locations P1 and P2, and show the very good correlation between the simulated and experimental values. So this is in line with what we have said before about accuracy of simulation for external fields. Typically is very, very good at predicting the external fields. So now we are ready to move on to the primary topic of this webinar, and that's the recent validations in a aircraft certification program. It was an experimental lightning program that was conducted on an aircraft wing test box, similar to the other two test boxes we've reviewed so far, but also simulations and experiments were performed on a full commercial aircraft that was primarily composed of CFRP materials for the wings. EMA 3D was used for all of the simulations. Comparisons were made between these results to validate the numerical techniques and parameters, and in general we see an excellent overall comparison in both magnitudes and wave shapes, which we will go through in some detail. these results for both the test box case and the full aircraft comparisons were presented at this year's International Conference on Lightning and Static Electricity, the ICOLS conference in Toulouse, France. So this was outlined earlier, but we'll walk through it again. But it's important to sort of set up a plan for incorporating your simulations into your certification program. And it's best that you establish this plan early and account for necessary validations of your, simulations. In this particular program, it was very useful to have engineering development tests, which we'll talk about very shortly. We have done test and simulation on a wingbox, which seems to be fairly common practice between the different certification programs to use an intermediate item, or an item of intermediate complexity between just panel testing or full structure testing. And we'll go through the test and simulation of the full aircraft, and we'll talk about how simulations are used after you have a validated model and how these simulations are done for the final in-flight aircraft. And this is used to establish your coupon threat levels. And then we'll briefly discuss also coupon testing. So the initial aspect of this, there's numbering associated with these different steps, and the numbers are correlated here for the titles. And so one of the initial steps is to do some engineering development tests and simulations. And for this particular program, a large number of samples were investigated, and we used those samples to identify many critical modeling features that we would incorporate into both the wing test box and full aircraft models. Some of those critical features include the conductivities of CFRP and ECF. They are anisotropic by nature, both the CFRP and ECF, and we used extensive number of samples to test and then to simulate, to compare to understand what conductivities are necessary to accurately simulate current distribution on the particular CFRP and ECF panels in this design. This was done for bare CFRP, plain ECF, and then the combination of CFRP with multiple grades of ECF. Another critical modeling feature is the contact resistance of fasteners. In the models that we put together for this project, we consider the contribution of every fastener to the current distribution. Oftentimes they are combined to form parallel resistances, and we incorporate that into the models. But in order to determine accurate values, like I say, an extensive number of samples were tested on, and we look at the contact resistance between CFRP panels and fasteners, the fasteners in ECF, and the fasteners to metal-like components, be it titanium or aluminum, depending on what area you're looking at. And as you might expect, there are a wide range of contact resistances depending on the types of fasteners that you're using, the installation techniques, and the types of materials that they're connecting to. So here's an example of a modeling technique that was established based on some of these initial engineering development tests. So carbon fiber panels are typically a stack of individual carbon plies. These plies are often separated by, tens of micrometers, and you stack them one on top of the other to get, several millimeters thickness of carbon, depending on your particular application. When using finite difference time domain technique, you cannot resolve the individual layers of the carbon, especially when you're using something like a 20 millimeter mesh. And so we developed a technique where we take a stack, which is illustrated on the left-hand side, the actual configuration. So this is representative of a heavy ECF layer, a light ECF layer, and then many different CFRP layers, which are all stacked together penetrated by a fastener, which then connects to some structure beneath that particular panel, be it the metallic rib or composite spar. And the technique that we use for this configuration is shown on the right-hand side, where we reduce that entire stack of materials into a single representative surface that we can then apply anisotropic or isotropic properties to represent the entire stack of materials. And this may seem difficult to do, and it took a significant amount of work to establish all of the appropriate parameters for using this bulk representation. But by doing this, it allows us to model the very large-scale aircraft in its entire form, including the wing, fuselage, and many other components, using this bulk representative method. And once we have reduced that stack to a single layer, we use a fastener of sorts to control the impedance between that top stack and the underlying structural components. So a very important aspect of modeling or understanding vehicles with carbon fiber is that, as we've already said, the carbon fiber is anisotropic by nature. And when modeling simple panels, or when modeling a test box that aligns very well with the principal coordinate axes, it's quite easy to apply anisotropic properties to those. But it is very difficult to apply anisotropic materials to a complex curvature, such as that occurs in the real aircraft wings, based on the staircasing, skewed orientation with three principal axes and curvature of it. It's not straightforward or simple to apply anisotropic materials. And so one of the goals of this effort is to use the test box to evaluate in a numerical fashion whether or not isotropic surfaces can be used for the full aircraft. And what was done is that two different models were created for this test box, one that uses anisotropic representations for all of the CFRP and ECF materials. And so this is reflective of the actual material properties. And then to see if we could use some isotropic representation where we average values or do some weighted average to estimate isotropic behavior of those materials. So now we're on to the test box model. It is a representative section of the actual aircraft wing. It contains 5 rib bays, as you can see on the right. It was constructed by Bombardier using production-type materials and construction methods. The skins and spars are of CFRP material, and multiple grades of ECF were used in the design. There are axis panels on the lower side, which is typical for aircraft maintenance and wings. And there are 2 types of systems were installed in a representative manner. There were 2 cable bundles that each had 5 wires, and they were routed throughout the different rib bays. And 1 hydraulic pipe was routed through the center of the box. To try and represent some of the metallic features associated or connected to the composite structure, they have a metallic leading edge that is provided here, and then there's also a strip of metal provided along the trailing edge, which they call the lightning diverter strip, and it is mounted to this trailing edge spar along this location. So within the model used M-harness to represent the wire bundles. We are able to include termination resistances and resolve the individual conductors by using M-harness. And 2 different configurations were explored. One that looked at current measurements on these wires so that both ends of the wires were connected to structure, and then one that examined voltage measurements so the wires were left connected at one end and then open at the other end to measure a voltage between the end of that wire and a nearby rib. For the experimental setup, a return conductor system, an RCS, comprising of metal sheets was built around the test box to negate facility effects, and a component A type waveform was used for injection purposes, and the amplitudes ranged from 2.6 to 10.4 kiloamps. Here are the different attach-detach scenarios that were used for this test box. 4 in total were analyzed for comparisons. There were 2 end injection cases, as shown on the left, where the injection was onto some braids that distributed the current through the leading edge, trailing edge, and center portions of the test box, and then evenly or distributedly taken off of the test box for detach. There was a case where current was injected onto the upper trailing edge side of the box and detached through the middle leading edge side, so that it's sort of a different current distribution pattern where current had to make its way across the carbon fiber ECF panels in order to get to the exit point. And there were also 2 fastener injection cases that were explored at 2 different fasteners on the lower end of the test box with a distributed detach for both of those cases. So now we're going to look at some of the results and validation that was done. We approached it with a direct comparison correlation technique, where we do a comparison of the peak amplitudes of the waveforms and an inspection of the waveform shapes. We did some comparisons of T1 and T2, where T1 is the time that the peak magnitude occurs, and T2 is the time where the waveform is at half of that peak value. In order to compare all of the results, we scaled the values to 20 kiloamps. So you saw before that the injections ranged from 2 to 10 kiloamps. In order to compare them, we scaled all of the results to 20 kiloamps. And some of the margins can be established in this way by looking at scatterplot comparison, which we have on the following slide. So this is an example of a scatterplot comparison that we use to establish an overall correlation and to develop margins. There's a lot of information on this plot. I'll try and walk you through it. On the y-axis is the experimental value, and in this case we're looking at current probes, so this is in amps, and you can see it ranges, the scale is from 1 to 10,000 amps, and the x-axis is the simulation value in amps. And so the red line is if the experiment and simulation were equal to each other. And then we have also provided plus or minus 6 dB lines. So the blue line on the bottom is minus 6 dB. So you can see that if the model estimate was 6 dB higher, it would fall on this line here. Or if the model underestimated by 6 dB, it would fall on this green line here. You'll notice there are 2 different types of data points. The green diamonds are the anisotropic model, and these orange squares are the isotropic model. As I explained before, we use 2 different types of models to evaluate. And you can see for both of them, overall, there is a very good correlation between the simulation and experiment. 80% of the peak values are within 3 dB of the experimental counterpart, which is, in my opinion, astounding. And 95% of the peak values are within 6 dB of their experimental counterpart. So for 150 total probes, we see this type of correlation for currents on the test box. When we look at voltages, there were 40 total data points, and it's the same type of plot, but in this case, we've also added plus or minus 3 dB lines because there is such good correlation between the simulated and experimental values. 90% of the values, the data points, are within 3 dB of their experimental values, and all of the voltages are within 6 dB between simulation and experiment. So by using these types of scatter plots, you can get a very top-level view, a quick assessment of the correlation between your simulated and experimental values. So now we'll look at some examples of the currents and voltages that were measured in the test box. This is an external current, so for a fastener injection case, current was measured on one of the detached braids here. Here we have shown the experimental curve in red, the anisotropic result from simulation in blue, and the isotropic model result in green. And you see an excellent comparison in both amplitude and wave shape for this comparison. Here is a section of rib that's just below the injection location. It's one benefit of doing a test box experiment and simulation is that you can modify the geometry to suit your exploration needs. And in this case, they drilled holes in different sections of the rib so that they could put Rogalski coils around those different sections and determine how the current would distribute through that rib as it passed through. Again, for the waveform and amplitude comparison, you see very good correlation, both with the isotropic and isotropic models. So this particular result is an order of magnitude down from the exterior one, where here you see 4,000 amps, you see 400 amps for this particular probe. So you see more discrepancy in the simulation to experiment comparison, but you still see very good overall prediction. This is a very interesting probe for a section of the trailing edge spar. The spar is CFRP material, and it is located on the exterior of the item, so that initially, one of the things I'll talk about real quick is redistribution effect of lightning. And let's see if I have one on the, okay. And so the redistribution effect of lightning states that at early times when fields are changing rapidly for a lightning waveform, the current is inductively dominant as an inductive distribution, so that based on the diameters of your components and the overall geometry, current will flow based on that. And then at later times, when current is changing less rapidly, it switches to a resistive distribution. And this probe and the next one are prime examples of that, and exemplify the ability of CEM to predict that. So when current is injected on this edge of the test box, and initially flows more or less over the outside of the test box, with current starting to ramp up on this composite spar section. But then because of the relatively high resistive nature of the CFRP materials relative to the metallic diverter strip or ECF materials, current quickly finds an alternative path and does not flow on the CFRP structure at later times. And so you can see that in the experimental and both simulation models, this behavior is captured. Then if we switch to an internal pipe, or I'm sorry, in this case it's an internal wire, we see the converse of that effect, where at early times the current is very low, but it continually ramps up to a point where the system is under a resistive distribution dominance, and you see the peak of the internal wire occur around 100 microseconds, which is very common in CFRP-like structures. And for this particular case, again, we see very good correlation between the experimental and simulated results. Here's a sample of the voltages. So this is for an internal wire terminated at rib 0, left open at rib 3, and the voltage was measured between the wire and rib 3. This is a fastener injection case. We see very similar amplitudes and waveforms for this voltage measurement. And so in conclusion, for the test box validation, we see an excellent overall correlation between the EMA 3D simulation results and the experimental results. Considering 200 total probes of current or voltage, 80% are within 3 dB and 95% are within 6 dB. And we notice in the different waveform examples that we see very good correlation whether or not we use the isotropic or anisotropic material representation. So this gives confidence that you can apply the isotropic representation to the full-scale aircraft, which was one of the goals from the beginning. So now we'll move on to the full aircraft test and simulation. The exact same modeling techniques and parameters that were used for the test box are applied to this full-scale aircraft model. It's part of the reason for doing the test box and engineering development test is that you establish what materials should be applied, and that approach was taken and followed. This is true for CFRP and ECF conductivities, and as I said, we use isotropic material representation in this case. It's also true for all fastener representations and contact resistances, and for the using simplified harnesses. That was the initial approach for this model. You can see in the image that there is an RCS routed around the aircraft model and shown by the blue lines, and this was included to negate facility effects for testing. So modified component A waveform was used, and 3 different attach-detach scenarios were considered, both for testing and for simulation, with the amplitudes ranging from 3 to 15 kiloamps. One thing you'll notice is that these waveforms are a bit slower in their peak time, whereas the test box and idealized component A waveforms peak around 6 microseconds. Because of the inductance associated with the full aircraft and the entire system, there's some delay on that peak rise time. And so you'll see typically these injection waveforms have T1s of about 20 microseconds or so. So for the full aircraft results and validation, a similar approach was taken as to that of the test box. We look at waveform peak amplitudes and do a dB comparison, and then also look at waveform shapes, T1s and T2s, to do a visual inspection. All of these results have been scaled to 200 kiloamps for comparative purposes, and again, margins have been developed using these dB peak comparisons and specifically the scatter plots showing those comparisons. So now we'll look at the same types of scatter plots for the current voltage and magnetic field results of this full aircraft test and simulation. So this is exactly the same kind of plot that was shown for the test box, where the experimental value is provided on the y-axis, the simulation value is provided on the x-axis, and the blue diamonds are the data points. And plus or minus 6 dB lines are provided to help illustrate the accuracy of the results. Here are some examples of waveforms for this particular program. There are currents that were measured on bonding jumpers and harnesses. So you see amplitudes of these range from, in these particular cases, about 2 to 5 kiloamps. So these, I believe, were jumpers and harnesses that were in exposed regions on the trailing edge side, which is why you see relatively high current values for these bundles and jumpers. But in general, you see good correlation between the simulation and experiment, both for the predicted peak magnitude and the overall wave shape associated with the transient. So here are the results for the surface magnetic fields, same type of plot, and this is using BDOT sensors along different areas of the external surfaces. We see in this case that all of the results fall within the plus or minus 6 dB margin. And as we've said a couple times throughout this presentation, that it's typically with better accuracy that external fields and currents are predicted with simulation. And these surface magnetic fields help to illustrate that point. Here are some comparisons of the waveforms for the magnetic fields. with amplitudes on the order of 20,000 amps per meter. We see good correlation between the peak value and the waveform. Here are the results for voltages. You can see again the majority of the data points are within that 6 dB range, and for values that range from a few volts to a couple hundred volts, we see overall very good correlation between the simulated and experimental results. Here are two examples of waveforms for the voltage probes. These are either for structural rib-to-rib voltages, where an artificial line was put in the aircraft to determine a rib-to-rib voltage, or to measure the voltage from an FQGS wire to a nearby structure. And you can see that the voltage is much higher in the case of FQGS because it routes over a longer span within the wing. So for the full aircraft validation, we see again an excellent overall correlation. For the 200 probes that were considered, 80% of the results are within 3 dB and 95% are within 6 dB. It was of special interest to consider why some of the results were outside of the 6 dB range, and we investigated these on a case-by-case basis, which we will talk about briefly now. It was found that nearly all of the predictions outside of that 6 dB margin were currents or voltages relating to the harnesses. Initially, a simplified harness was used, as shown in the lower left-hand side. This was done because initially this was going to be a direct defects investigation, where we were concerned with currents and voltages in and around the fuel tanks specifically. But when the opportunity came up, they decided to add probes on the available harnesses to have a brief look at the indirect effects aspects. And it was discovered that this simple representation using a bulk diameter and parallel resistance combination of those particular cables was not adequate to accurately predict the amounts of currents and voltages that would couple to those harnesses. So what we did was go back and define much more detailed harnesses to represent the cables in the leading and trailing edge sections of this particular model. So whereas bulk representations on the left-hand side were initially used, we went back and determined the number of cables, the types of cables, and their routing locations, and incorporated a more detailed harness model. So when we did that, as you can imagine, there was drastically improved correlation between the simulation and experiment, whereas we had on the order of 10 dB discrepancy before, it improved to less than 3 dB discrepancy. And with the resolution within the M harness model, we were able to just select a few of the conductors to probe, whereas if you consider these two harnesses connected at this location, and there's a branching just before that termination, and a majority of the cables are in this fatter conductor, and just 4 of them were in this one, we're able to resolve that within M harness and measure just a small portion of those cables for bundle representation. And you can see with that result that there is a very good comparison between the simulated and experimental value. This was also done for pin voltages, and here's one such example for a 20-gauge TSP cable. The VOC was measured and simulated, and we see very good correlation between those two. So by updating the features of the harnesses, you're able to more accurately predict the currents and voltages that will flow on those harnesses and cables, which makes perfect sense. So here are some conclusions from this validation approach. EMA 3D can be used, and CEM simulations in general, to support a certification program. Some of the benefits are that they allow a complete understanding of the lightning response for a complex aircraft system. Engineering development tests are considered to be an essential and crucial step to quantify critical parameters and modeling techniques. The test box I consider also an essential step between panel testing and full aircraft testing because it allows the complex study of connections between skins, spars, ribs, and other system-like components without the complexities of testing an entire aircraft. It allows you also to further develop your test methods and the initial application of your modeling parameters. And then by having a full-scale aircraft or large-scale wing portion, you can ensure in a very convincing fashion that your modeling techniques are validated and do apply to your specific aircraft design. So once you have validated models, after all the simulations have been done and compared to test results, you need to do final certification runs, and this is using your actual in-flight model. And by doing this with an extensive number of attachment scenarios, you have a very high confidence that you are predicting the worst case values of lightning threat to your particular vehicle. And this will give you both conservative and realistic threat levels for your coupon testing. And once you have this full analysis of these different attached, detached locations for your in-flight model, you have a very complete picture of the lightning response for your entire aircraft. And then here's just a very brief slide describing or illustrating how you would take those simulation results from your final in-flight certification simulations, and then you would use those results and apply them to your test coupons. So these threat levels would be applied for these test coupons with a very high confidence. So that is the information that I have for this webinar. Again, I thank you all for joining and for listening. We reviewed different applications of CEM simulations for lightning, both historically where it has been used and then also a more recent effort. And we looked at a lot of the results from that certification project and the overall validation effort. This is the first of a webinar series that we are trying to host here at EMA, and we intend to have more in the near future. And you can keep checking EMA3D.com, and we will continue to update you with those plans. And if you have any questions about this content or electromagnetic questions in general, we'd be happy to discuss those with you. You can email me at Cody@EMA3D.com or Jennifer@EMA3D.com or Tim. Again, thank you all for joining, and that concludes our webinar. On this last page, I have a list of references for on some of the data and information that was provided in the webinar.
Hi, Cody. This is Jennifer.
Hi, Jennifer.
Hi. We have a question. Do you want me to, do we have time to answer it?
Yeah, I think we're still under the hour, so if we want to address a question, I think that'd be fine.
Okay, so the question is for the airplane level experiments, the 6 dB achieved measuring individual fasteners or at the joint level?
6 dB achieved measuring individual fastener or at the joint level. I'm not quite sure I understand that. So 6 dB achieved at measuring individual fasteners or at the joint level. So I think maybe this pertains to if we're considering measurements on an individual fastener or over an entire joint. And in the case of the aircraft, the full aircraft, it's not possible to probe an individual fastener just because of the construction techniques. And so any time that we measured a bulk current, it would have been around a joint level. So it would have been the entire section of joints that combine two structures. And so I hope that's what that question was addressed at and that I answered it.
Okay, I have another question. Could you tell us the time consumption and PC resource requirement of your modeling?
Oh, that's a very good question. So for this full aircraft modeling, we used parallel processing and gradual epsilon scaling speed-up techniques, and we have a cluster that has 160 total cores. And when we use that full cluster, we have a simulation time that is typically on the order of 1 day for a component A lightning simulation that runs out to 500 microseconds. And I believe the total memory associated with those type of models is about 20 gigabytes is the size of the problem. So you do need typically larger than just a desktop, unless it's a very powerful desktop, to run those kinds of simulations. So it looks like there's another one about cable harness modeling.
Mm-hmm.
And so what is the key element on cable harness modeling? That's a tough one to answer just generally. But what we found to produce very reliable results in simulation for harness modeling is that you have the routing of the cable done accurately, so that you have the accurate representation of the structures or geometry around it, so that you're using the appropriate coupling mechanism, whether it's magnetic fields or diffusion or resistive distribution. You're accurately reflecting that, and then you have accurate routing of your harness, and then also a accurate representation. Both if it's magnetic field dominance, then you have to resolve the diameter of that cable, but if it's a resistive dominance, if it's something that's well shielded, then it's resolving the parallel resistances of the cables that greatly impacts the coupling response for a particular harness. And so I think in the case, what I had shown here for the improvement of the harness models is that we were not able to resolve all of the routing details for those initial bulk representation of the harnesses. And so then by breaking out the individual conductors, we more accurately reflected the routing of the cables, and that gave us the better results to compare with the experimental values.
So we have another. Do we have time for another question?
Yeah, I mean, people are welcome to leave if they like. They do not have to stay on. But I think that we have the webinar scheduled for an hour and a half, so that we can entertain questions for the next half hour, and I'm okay to do that. So I think that if there are other questions, we can address those.
Okay. So we have another question. What's the suggested tools for simulating radiated emissions from cable harness in addition to EMA 3D?
So what we use for that is the integrated M harness. And so that allows the detailed representation of the harness. And if there is other structures around it, you would want EMA 3D as well. But detailed representation of the harnesses is done within our transmission line solver M harness. And it can be done standalone in the M harness simulations, or it can be done integrated with EMA 3D, where the results are co-simulated, so they're done at the exact same time to look at those emissions. Well, I'm not sure if we're going to have any more questions, but again, I'd like to thank everybody for joining this webinar. It's nice to get a large group of engineering professionals together and review topics like this. If you have additional questions, or other things you'd like to discuss, please do not hesitate to email us or visit our website for additional information. Again, it's Cody@EMA3D.com, Jennifer@EMA3D.com, or Tim@EMA3D.com. And be on the lookout for more webinar series from EMA in the not-too-distant future. Okay, I think that concludes this webinar session. Thanks again, everybody.